So all right, so the first chapter following along with our textbook for the semester covers a bunch of topics, but it's just an introductory chapter to the topic of fluid mechanics, okay? So we're going to talk about definition of fluid, blah, 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 blah. There's a lot of topics. Let's just jump into it. So what's a fluid? A fluid is a substance that continuously deforms when subjected to a shear stress. Do this. Put a plate and sandwich some substance like a fluid in between. Okay? Take that top plate and the bottom plate be rigidly attached to the floor or something. Take the top plate and pull on it with the force F. If the plate starts moving and after some time continuously moves in the X direction and horizontal is just being pulled along at a constant speed V, then what you have in between is a fluid. And it may be something like air. It would have a small force to go at a fast speed. Or it may be something like oil, would need a larger force to go at the same speed. Or it may be some other very viscous substance. You have a sense of viscosity, okay? Then it would need a much larger force to go at the same speed. But what's happening is it's being sheared. It's being subjected to a shear stress. Okay. So gases and liquids are fluids, but if I put a solid in here, what happens? Well, it doesn't continuously deform. It deforms, but it may undergo a sort of a stretch. Maybe this point moves over a distance delta x to that point when you subject the top plate to a shear force, pulling it. It just deforms like that, but it doesn't continuously deform. And then if it's an elastic solid, I haven't stretched it too far, if I relax that force, it just goes back. True? So that's the difference. Solids are not fluids. Okay. What about compressible substances? Well, compressible substance or incompressible, meaning not compressible. So a compressible substance has the density is not constant. It's variable. So it can be changed. Often the density is a function of pressure. So if I typically boost the pressure, density increases. Right? But it can also be a function of temperature. If I heat something up, it typically expands. So for compressible substances, often we think of it as a function of pressure only, but temperature can also affect the density. All right. Incompressible, the density is constant. I can pressurize it, density doesn't change. I can heat it up, density doesn't change. Steady or unsteady? Well, does a property change as a function of time? Or does it not change? If it's steady state, steady, it doesn't change with time. Now, you can have some problems where certain properties change with time and some don't, but just think about if it's steady state, all of the important properties are not changing with time. Uniform. That means if I move from this location to that location to that location, and I ask the same question, I get the same answer. Is the density the same? Is the density at this point the same as the density at that point? Then it's a uniform. That makes sense. True? All right. Or I say the velocity. This velocity is the same at all three. Uniform velocity field. External flow. So a lot of problems deal with flow over a surface, let's say a wing. And so we have fluid flow approaching it, and the flow is external to the surface that it goes around. A ball in the air. So you have air and you have a ball. Or another object like a rocket. Or a car. You have external flow around the car. Those are all classes of problems. Internal flow, well, in a flow in a pipe or in a duct. So duct doesn't have to be rectangular, but you have flow inside something that's containing it. Typically it's one-dimensional. So pipes or ducts. Also, a lot of times you need the pipes to split, pipes to join. You have elbows, you have T's, turn the pipe flow, direct it here, direct it there, restrict it. So I have a valve, maybe or a damper, and I can close it, partially close it. So all of these are associated with internal flow. No slip. I'm just following some of the topics. Some of these are pretty straightforward, aren't they? But no slip. So I'm interested in the fluid at the solid fluid interface. So let's say I have, some surface like this, and I say, this solid right here I have is stationary, so the velocity of this solid is 0. But I have fluid flowing over it. What about the chunk of fluid that's adjacent, infinitesimally close to, the solid particle or point? Well, the velocity of the fluid that's at that interface between the solid and fluid has the same velocity as the solid. It's no slip. There's no slip between them. So they move at the same speed. So if one's at rest, the other's at rest. If one's moving, the other's moving. All right. Boundary layer. Well, let's go back to this problem here. But let's make it a flat surface. And let's make it a knife-edged cutting, thin, very thin, which I've exaggerated the thickness by showing you. But it's like a knife-edged, razor blade edge surface. And I have fluid flow coming at it. All right. This thin razor surface, this solid surface, is not moving. Just the fluid's coming at it with a speed V infinity. That's called our free stream speed of the fluid. Why do they put infinity? Because it's far away from the solid, way over here, it's the same speed. It's not affected by the presence of this very thin little surface. Got it? So this speed right out here is V infinity. This speed out here is V infinity. Far away from the presence of the solid, the fluid is a uniform speed. Now, what about the speed of the fluid right here on the surface, right here on the surface, right here on the surface? Well, from the no-slip boundary condition, we know that that speed is 0. Well, we're interested in maybe showing the speed on a scale moving up into the fluid y distance away. We'll typically measure x from the leading edge and y, the perpendicular direction, y going into the fluid. So this, we'll talk about y going here and y going there. You could probably sketch the velocity and say, you know what? When y is 0, the velocity is 0 at all 3 points. Far away, what's at large y, far away from the plate, it's V infinity. The magnitude is shown by the length of that line. It's V infinity. They all have the same magnitude of the speed. But what happens is somehow there's a transition. True? And that's called the layer of fluid near the boundary of the solid that's affected by the presence of that solid. That fluid, all up here, it all has the speed V infinity. All up here it has a speed V infinity going that way. Sometimes they'll show it that way with little vectors. But then it comes down here and there's a little transition like that. Okay? So this right here, this distance is called the boundary layer. Now, what do you think as it goes further down the plate? Do you think that thickness of that boundary layer gets larger or smaller? It gets larger. And so it's a little larger here, it's a little larger there. So as you go further down, there's a transition. So the thickness of the boundary layer can increase. And so that's that transition region in the fluid between the no slip at the solid surface and the free stream far away from the solid. Well, we already mentioned about flow between two parallel plates where one top plate is moving. You could also have, let's say, a knife-edged plate like this and a knife-edged plate like this, and the fluid flow comes in like that. Well, what will happen is you can identify the center. I don't know why they use this CL. I never figured that out. Why do they use the CL like that? Do you know? Center line. That's right. Center line. Anyway, it's symmetric above and below the center line. But what you have is you start to grow the boundary layer out. True? And if you have it long enough, what will happen is the boundary layer from the bottom plate and the boundary layer from the top plate will eventually join. And then past that point where they join, what do you suspect? It's not like the boundary, they meet up. And so in this region, the boundary layers are now fully joined, and the velocity profile, if I wanted to plot it across, let's go down here. I would have a velocity profile that may have a shape like this. No slip at the boundaries, maximum at the center line, and it has to taper off. If I asked, well, what's the profile here? You know what? It looks the same. I didn't draw it the same, did I? Let me try again. It has the same profile, velocity profile. So what we're doing is at every distance, let's call this y, we're plotting the magnitude of the velocity. It's maximum at the center line. It goes to 0 at the boundary. But what about over here? It's a little complicated. But over here, you have, let's try and draw it right here. You have, and I'll change the color to red. You have in the core, it hasn't felt the presence. And so this is all V infinity. And then you have a sharp transition down. So it's blunt in the core and then a transition. Okay? Makes sense? So we talk about velocity profiles, talk about boundary layers. Need to talk a little bit about shear stress. How many people know there's a difference between the fluid air, the fluid water, the fluid oil? Those are all three fluids. And what happens is some of these are characterized by not only a difference in density, but a difference in another property, viscosity. Okay, viscosity. Brand new property for you, isn't it? Viscosity. Well, there's a relationship between the shear stress and the rate of change of the velocity with respect to distance moving away from the solid interface into the fluid. So if I was sitting here and I drew that solid surface, I introduced a direction y, I have the concept of a boundary layer. Okay. Now, way out here for large y, let me increase y. Okay. I can think about having u, that's the x, the magnitude of the x component of the fluid velocity as a function of y. Okay. If I said out in this region, calculate du dy, could you do it? Du dy. That's the rate of change of u in the direction of y. As I increase from this location, if I increase y, how does u change? Does it increase, decrease, or stay the same? Stays the same, true? So what is this derivative? It's 0. Okay? All right. Come right into this region right here. I want to evaluate du dy at this location y. It's the slope of that line, isn't it? So, is du dy, if I go in the direction of increasing y, does u increase or decrease? Increases. So this is positive, true? The derivative, du dy, is positive. True or false? True. So what I have is a relationship where the shear stress, one fluid layer acting on another fluid layer, how that transmits this force per unit area called stress is equal to du dy, how the velocity is changing, and a property, viscosity. Okay, so if I come back to this guy and I cut the layer right here, let me try this color. I have some fluid that's on the top and some fluid on the bottom of that cut line. True? Okay. The fluid on the top feels a force in the negative direction because of the slower fluid below it trying to pull it back. The fluid on the bottom feels an equal magnitude force, but in the positive direction because the faster fluid on top is shearing. It's pulling it with the shear stress in the positive x direction. This is the equation that relates the shear stress to the velocity gradient. Okay. What is this property? It's a fluid property known as the viscosity. Okay. So we could go back. I know this was a plate where you have free stream going over it. You could go back to the fluid where I have an equal thickness L and a top plate pulled with a constant force or a constant shear stress applied because it's force per unit area. And then I have different fluids in here, true? So what about the ventral speed of the top plate? If I had air in here versus water versus oil, which top, for the same force, same unit area, which fluid will give me a faster top plate speed? Air or water or oil? Air, it's less viscous. And the oil, especially cold oil, think of cold oil, it's very viscous, right? Everybody, if you ever had the experience of pouring oil out of an oil can into your car on a very cold winter day, it looks different. Or very hot day and the oil has been warmed because it's been in the sun or something. Or if you've ever pulled your oil plug and drained your oil on a cold day without the engine being warm versus when it's hot, don't burn your fingers or anything, but you see that the viscosity of oil changes strongly with temperature. All right. Now we'll talk about different flow conditions. One is laminar, the other is turbulent. Probably you've experienced these terms before in your discussion and maybe even other classes. Well, laminar talks about flow in layers. So if I have flow going this way, you could think about each chunk of fluid staying in its layer. Staying in its layer. So this chunk here, maybe if it's color-coded blue, if I took a picture every second, it would just be in its own layer and it wouldn't jump between layers. Okay. And if this one was color-coded green, it would stay in its layer. That's laminar flow. What about turbulent flow? Well, take that idea of layers, and you take the blue chunk, and it starts here, maybe it stays there, and then it's over here, then it's back, then it's over here, and then it's down here. So it's mixing. Okay, it doesn't stay in its layer. Just like the green would be going back and forth, jumping around. Okay? So this is more disorganized. It's more random. What type of flow condition would you like to have if you wanted to promote mixing? You would want turbulent flow. Okay. If I said I can have either slow flow in a pipe or fast flow in a pipe, right? Which one would be more conducive for laminar flow, where the flow stays organized in its layers? Slow or fast? The slow flow is more laminar-like. The fast flow is more turbulent-like. Okay? Now, also, if I had flow in a pipe right here, and every now and then there's a bump on the pipe. Let's say they put a little bump in the walls of the pipe, okay? Like that. It's not going super slow, it's not going super fast. Those little bumps on the walls of the pipe, would they help promote laminar flow or help promote turbulent flow? Turbulent flow, because it's trying to trip it, right? And then once you start tripping, then the fluid starts rotating and being turbulent. So these bumps or changes in the flow direction locally caused by bumps can have an effect into the whole flow region. They promote turbulence. Okay. Well, there's a dimensionless number called the Reynolds number. The Reynolds number is defined as a ratio of inertial to viscous forces. A chunk of fluid feels as it's flowing through a flow system, okay? Forget about being accelerated. We're doing steady flow, okay? So time average, steady flow. A chunk of fluid feels two things. One, it's got a little chunk of mass, and it's got its own little inertia, and it can go where it wants to go because of its inertia. So if it's currently going in this direction, it wants to stay going in that direction. If it's currently going in this direction, it wants to stay in that direction. And if it's going in that direction, it wants to stay going in that direction. It's the inertia of the little chunk of fluid. Okay. What about the viscous forces? Well, the viscous forces are not only does the little chunk of fluid, it's surrounded by other chunks of fluid. Right? Okay. So they are all going somewhere, and they want to carry that little blue chunk of fluid in the direction that they're going. All right? Maybe a simple analogy is this is kindergarten. In first grade, I went to a school, they had a long hallway and classrooms off of the hallway. And you had doors out, and I mean this was long hallway. Out of the rooms like this, they would open up into the hallway. And down at the end, they had doors that went out of the building and a driveway for the buses to pull up. And because kids can get lost, and they need to get the kids on the right bus, so they would say, okay, bus number on the intercom system, bus number 32. All children that need to go to bus 32, teachers let them out of the room, go down the hallway, get into the bus. Okay, well, every little kindergartner that I ever went to that school just formed a nice little line where they came out like that, they came out like that. True? And then they came out like that, they came out like that, they came out like that. Or is that not the kindergartners you knew? Oh, they saw a friend, and they want to sit next to that friend. Oh, they want to go here, there. Oh, boy, it was chaos. But once the chaos ended, bus 32 was filled up. They shut the door of bus 32. It pulled away in another bus. True? That everybody, little kid, wants to go there, even if they got to push the shove to get to their friend in the hallway. Or maybe they decided they left something in the classroom across the way, so they make a big trip. Well, another analogy with kindergartners is anybody ever been in a downtown area and they're moving a bunch of children across a busy street? True? What do they do? What does the teacher do? Tells all the students to do what? Get your hand and hold hands. Guess what? It just greatly increased the viscosity of the group. And that's the viscosity of the group. So your little independent inertia of each kindergartner is going to be locked down by high viscosity hand-holding operation. So anyway, when you have a high Reynolds number, the inertial forces or pressures or effects are high, you're going to have more turbulent flow. And when you have low Reynolds number, that means the viscous forces are more severe, more stronger to make it a smaller Reynolds number. Hence, you have laminar flow. Okay? All right. We're going to talk more about Reynolds number. This is just an introduction. Mach number is another dimensionless number. So if you compute the Reynolds number correctly, it's dimensionless. If you compute the Mach number correctly, it's dimensionless. Okay? So the Mach number is the ratio of the speed of sound of an object in the fluid divided by the speed of the sound in the fluid, the local speed of sound. C is a letter that we'll call for the speed of sound, or use for the speed of sound. Now, when the Mach number is less than 1, it's subsonic. When the Mach number is 1, then the object's traveling at the speed of sound, it's sonic. And yes, you can have supersonic and hypersonic. So the Mach number much, much greater than 1, Mach number greater than 1. There's also transonic, it's around 1. Okay. So that's another dimensionless number that we'll talk about later in this class. How many people have heard of Mach number? Yeah, right? Sure. How many people heard of Reynolds number? Good. Okay, this is just a quick review of thermodynamics. What's the system? It's the focus of the study. It can be a chunk of mass or it can be a chunk of volume. The surroundings, everything that's not in the system. And how do you separate them? With a boundary. Often you use the dashed line. The classic closed system, you can't leave thermo, right, is a trapped amount of gas in a piston cylinder apparatus. There's our system. That system can be compressed, it can be heated, it can be expanded, it can be cooled. A lot of things can happen to that system. Another open system, maybe you're analyzing a pump. Pumps typically are like this. They bring fluid into the middle of them, they throw it out on the edge. And you want to analyze that system, so you put a control volume, which is an open system, because there's mass flow rate across that boundary of the system and mass flow rate across that boundary. You also have probably power, shaft power, driving the pump. There's many analyses of turbines, pumps, nozzles. This one, you've sat through this lecture I don't know how many times in your life. Chemistry, physics, maybe statics. How many primary dimensions are there used in science and engineering to describe science and engineering? All you need is 7. 7 primary dimensions. The first few we use a lot. Mass, length, time, temperature. These others, amount, we don't use as much, but we do. Current, we use. Light intensity, never. My whole life, light intensity. Didn't need it. Got it? All right. But if I was saying, now that I understand the dimension, I can describe in either the SI or the USCS units. So, what would be the SI unit for the dimension mass? Kilogram. What would be the SI unit for the dimension length? Meter. Time, second. Temperature, degrees C or Kelvin. Amount, kilomole. Current, ampere. And it's candela, but we don't care. Okay? Now, this was for the SI, which is MKS. It's just the majority of what engineers use. But if you go to the chemist, they're not going to say kilogram. They're going to say, take the kilo off, gram. They're not going to say meter. They're going to say too big. cm, centimeter. Right? Second, degrees C, K, mole instead of kilomole. Take the kilo off. And ampere and candela. Now, why did they have, sometimes people say MKS? Well, mass. No. What is the MKS? What does the S stand for? Second. Good. We got the S down. Good. How about the M or the K? That's right. Meter, kilogram, second. MKS. Okay. What about CGS? Well, we got the second. G, gram. C, centimeter. CGS. Sometimes you'll see that. Now, there's another system of units. Some people will still say it's the British system of units or the English system of units, but it's only used in one country. We live in it. United States and Guam and maybe a few other little places, but that's it. You go to England, and some people can converse in pounds and mass of pounds, but most of it is in kilograms and centimeters, things like that. Okay. So, what is this? It's the United States customary system of units. It's what we use still on the streets, out there in practice. Okay, so what is our mass? It's a pound. What is our length? Foot, second, degrees F, Rankine, a pound mole, an ampere, and a candela. What's the difference between a pound mole and a pound? Well, if I don't have a kilo of a certain amount, I have a pound of a certain amount. So it's going to be off by a factor of about 2.2. Okay, because that's the relationship between a kilogram and a pound. True? Somewhere in there. Okay. How about, what's this F and this P and the S stand for? Foot, pound, second. Exactly right. And then you could also do pound second, but what's the I for? We still use inch a lot. Inch with the period. Inch, whoops, I've got it in the wrong place. Pound, inch, second, degree FR, pound, mole, ampere, candela. Now, somebody says, I heard that there's some confusion between what this mass is. Is that a pound mass or a pound force? Okay, it's a pound mass, so put a big lowercase m on it if to really distinguish. Sometimes you'll see LBF and LBM to be real clear. But sometimes you'll just see LBS, pounds, like it's a plural. Well, you're not supposed to pluralize things, right? Like, this is not meters. You just put meter. Don't pluralize it, right? But sometimes you'll see pounds, especially on a stuff you buy in a store. You'll look on the label and it's like, oh, yeah, they're selling it to me in pound or pounds, right? Okay. So that's just the pluralization. So some books make a big deal and they say, hey, in the United States customary system units, they don't use mass, they use a force. Don't get bogged down. The USCS is going away. I have a lot of metric wrenches for my cars and automobiles. Since I forget what year, there's been no 9/16 inch anything on a US-made car, right? Even the company that makes rebar that is in Seguin used to always buy your inch and 3/4 inch reinforcing rod, something so common. But they transition. They're not going to refuse to sell to a customer, but they're going to sell their rebar in centimeters. And if you want a 1/2 inch, no sweat, they got it for you. They're not going to argue with you, but it's all made and all measured in centimeters, in millimeters. Okay, so the industries are moving, but different industries have already gone. Some are really going to be a while, and some are really going to be a long time moving. Okay. How about secondary dimensions? Well, things like speed, well, it can be related to the primary dimensions. What's speed equal to? A ratio of length over time. True? What is area a ratio of? or not a ratio, but a length times a length. True? Product of length to length. What about force? Oh boy. Force. It's a mass times, well, no, we got to get it down to the basic 7. Length divided by time squared. Is that right? All right, what about work? Mass times length squared divided by time squared. Professor, I thought this whole class was just going to be an easy breeze. Now you're making me remember some of these hard things. All right, no sweat. In the SI system of units, speed meters per second. Let's dispense with the CGS. Let's just go MKS. How about area? Meters squared. How about force? Kilogram meter per second squared, also defined to be a Newton. How about kilogram meter squared per second squared? Oh, but that's a Newton times a meter. That's also a joule. True? Good. How about for the U.S. customary? Well, this would be foot per second, foot squared. What about force? LBF, pound force. All right, but how do you break it down? What's an LBF? It's an LBM, foot second squared. If I had my clickers, I would be here saying yes or no. 8% of your grade is going to be on these type of questions. I would say A, true, or B, false. How many people are so emotionally self-confident they can raise their hand in front of their peers and risk being embarrassed if they're wrong? I know this is a lot to ask. Right? Or they want to know, Professor, only let me answer these type of questions with a clicker. I can do it below my belt. You know, I'm just kind of down here. Nobody will see if I push A or B. How many people want to participate? Can you participate? You want to participate. Very good. I got to vote. All right, I'll take all the truths. This is true, as I've written. 1 pound force is equal to a pound mass. What did I write there? That looks like an H. Foot second squared. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. All right. False. Smart people are 1, 2, 3, 4, 5, 6. Would anybody want to change the vote? You're good, right? You're good. It's false. Oh, man. Why is that false? It looks parallel. What's a Newton defined as? Is a Newton defined as a kilogram meter per second squared? Is that the definition of a Newton? Yeah, that's right. Okay. What's a pound force defined as? I don't even live in the United States. Why do you torture me? All our books are SI. I want to go SI. I've written the president a letter. He's going to SI. He's responded. We are going. I don't need to know these. Pounds are not needed. I'm working overseas. I'm going to Europe, Japan, anywhere. I don't want to deal with these pounds. All right, I'm going to have to come back to this one, but it's false. I'll get to it. I will. This lecture, I hope. Dimensional homogeneity. What does that mean? These words are getting longer, Professor. Well, it just means that if I'm going to add two things, they have to have the same dimension, right? If I wrote and I said, here's a length, add to it a length per unit time, you should say, what? It ain't going to work. True? When do you use dimensional homogeneity? To check your work. It's an extremely valuable tool. How many people have solved engineering problems and say, oh, let me check, and my units don't work out? You're doing dimensional homogeneity, making sure your units are consistent, work out. How do you convert units? we recommend the 1. True? So, a unit conversion factor. If somebody said I have a length given to be, 48 inches, and I want you to convert that length to feet, that's an engineering challenge. You want to make sure and not do it incorrectly. You take that equation, you multiply that side of the equation by 1. Is the equation still correct? Yep, it sure is. And now you can work through it. So, you just recall that 12 inches is defined as 1 foot. Is that true? You've got to get to a truthful statement. Is that absolutely true? I can take it to the bank. 12 inches is 1 foot by definition. Good. Now I can rearrange that by either going and taking the 1 foot and dividing by 12 inches, which will make a 1 on this side, or taking the 12 inches and dividing by 1 foot, and it'll make it 1 on the other side. I can use either version A or version B of 1. True? Which version should I use to right here? Should I use version A or version B? So I multiply by 1 foot is exactly 12 inches. Cancel the inches. Divide. True? Oh, not true? Hold it, which is true? This is true or not? This is true. Now, that's too familiar. So let's do something that's a little less familiar. How many people know about what an acre is? What's an acre? It's a measure of area of land. Okay? How many people know how many square foot it is? 40, I forget. Okay. How many know what a section is? Section of land. You're a rancher. You're going to buy a section. What's a section of land? Come on. You have high aspirations. You're going to get a good job. What's a section? It's 1 mile by 1 mile. 1 square mile. Okay. So if section's 1 square mile, mile squared, how many acres are in a mile squared of land? Louisiana Purchase was chunked off. You ever fly an airplane over Indiana, Illinois, Iowa, Ohio? Anybody ever fly, look out the window and look down? What do the roads look like? Square on a grid. Until they hit rivers and they got to, get around a river or have some distortion. But it's gridded up. It's gridded up in 1 square miles. True or false? True. Somebody's lived outside of the state of Texas. Texas was not part of the Louisiana Purchase. We have cow trails for our main roads. Wagon trails. Okay. There's 680 acres in 1 square mile. I know that. You don't have to know it. Now trust me. So somebody says, I have a ranch of, 43,000 acres. How many square miles is it? How big is it in sections? Well, what you do is you'd say the area of the ranch is that. True? Let's multiply by unity to get the conversion factor down. What version of unity do we want? Well, let's get 680 acres and then 1 mile squared, or 1 section. Well, we don't cancel the 680. We've got to cancel the acres. And you do the math. I have no idea how big 43,000 acres is. But you have a calculator? You're going to run it for me? I don't have. It's beyond my wildest dream to own a ranch, 43,000 acres, right? But out west Texas, I'm sure you can buy one. How many sections? 63.2 sections. Look in the newspaper, you probably can buy a ranch bigger than that. All right. Mass. What is mass? Give me a kindergarten. You're going to talk to a kindergartner. Tell me what you would tell to a kindergartner. This is what mass is. I would say every object has mass. This is an object. It has some mass. The mass of the object measures its resistance to its change in its current state of motion. If it's at rest, it wants to stay at rest. If I want to change it from rest, I'm going to have a big force. True? If it's already moving, like a train has a lot of mass, and I want to stop it, it's going to take a lot of force to stop that lot. So mass is a measure of its inertia, resistance to change in its current state of motion. That's what mass is. A lot of people look at it and they think about this equation because that is the constant of proportionality between force and acceleration, right? But I forgot. What number of Newton's laws is this? Is it the first? Is it the second? The third? The fourth? The 18th? Second. It's the second. There you go. I don't ask always hard questions. There's a lot of questions that are that easy. So this is the mass. It relates the force applied, or the sum of the forces, the imbalance in the forces, to the resulting acceleration. So if I have a large mass, I'm going to lead a large force for the same acceleration. Or think of it another way is, if I have a large mass, I apply a force, I may have a very small acceleration. I'm attracted to the Earth. The Earth is attracted to me. It's called gravity. There's an equation, Newton's law of gravitational acceleration, attraction. Have you seen this equation before? It says that the force between mass 1 and mass 2, okay, is equal to a constant times the magnitude of the mass 1, magnitude of the mass 2, and what's r? The distance separating the two masses, and you have it squared. So if I look at the Earth's surface, basically I'm on the Earth's surface. R is pretty well not changing. I may climb a mountain. I may even go 30,000 foot out into the airplane high above the alt. But you know what? It's minuscule compared to the radius of the Earth. Okay. So this R stays constant, and the mass of the Earth stays constant, and that G is a constant. So the force just turns into a bunch of constants times my mass, m2. True? Have you seen this equation? F on the surface of the Earth, the forward, downward directed force that I feel, gravitational traction or acceleration, is equal to mg. If I take myself, or I take any object, this object, and I let it go, and I let it fall freely to the surface of the Earth, right? Okay, that's a free-falling mass. How, if I drop it, what does that say about its initial downward velocity? 0. I'm releasing it at rest. So the velocity, it starts at 0, but it continually increases. True or false? True. Okay. The velocity continually increases. It's falling at a faster speed as it goes down. How about the acceleration? Does the acceleration continually increase? I'm so glad you passed dynamics. Do you know it's not that hard a question, but I can trip up ninth graders all day on types of questions like that. Right? Well, yeah, no, this is a constant. It's free falling. And so on the surface of the Earth, what is that free falling acceleration? It's given the name g. There's a symbol g for it. And if the SI units, the number is, and I forgot the units. Meters per second squared? Or is it meters squared per second? You're good. You're good. There's a lot of people still trying to pass dynamics that probably got that wrong. Or in the U.S. system of units, it's 32.2 foot per second squared. Both of these are G. Could I use that? Could I use that to make a unit conversion factor if I needed one? So that 9.81 meters per second squared is the same as 32.2 foot per second squared. Is that true? And I could use that in a lot of different ways. As long as I know that's a truthful statement, I could use it. Okay. So what again is the name of G? What should I put right here? Earth's gravitational acceleration. Something about acceleration, because the acceleration is constant when I drop it. Okay? Or sometimes we just call it gravity. A lot of times we don't drop objects. This object's been sitting up here on this table the whole lecture. Has it been free falling? Most objects that I know are sitting there stationary on the surface of the earth. True? So that brings us the concept of weight. So somebody says, I know how to calculate weight. I'll take the mass and I'll multiply it by Earth's gravitational free fall acceleration. The first time you see that, you say, hold it, it's not accelerating. It's just sitting here. And I want to know its weight. Its acceleration is nothing. I know. But G is 9.81 meters per second squared. Put it in the equation. Trust me, you'll get newtons. True? Okay. So in the SI, we can calculate the weight of an object. Somebody who's speaks SI, they don't want to deal with pounds. They're just here for an education. They're going back to a country where it's all just SI. Those people that are in this room, answer this question. Tell me what is the weight of themselves, or estimate the weight of an object. Estimate my weight. Okay? Who would like to estimate my weight if you're conversant in kilos? Anybody? You will? Tell me. 85 kilos. All right, 85 kilos. Oh, is that kilo Newton? It must be in kilo Newton because the weight is in Newton. I'm confused. 85 kilograms is my weight? The SI is not perfect. We have nothing to be ashamed of in the United States. Nothing to be ashamed of, absolutely. And so a lot of times they'll put a KGF. Just like we use an LBM and an LBF, they use a kg without the M and a kg. Okay, yeah, I'm talking weight. It's a force. Got it? Now, if I take my 85 kilos and I park it on a scale which reads out newtons, my weight in newtons is not 85 newtons. 9.81 is close enough to 10. What's my weight in newtons? Around 850. True? Right, close enough to 10. Thank you very much for participating. That's very good. Now, the thing is I'm in the U.S. That's SI. I'm in the U.S. All right. Does this equation still work? Okay. I take 1 pound mass. Okay. And I put it on a scale. The scale, but I have G. G is 32.2 lb, not lb, it's foot per second squared. All right, what is the weight? I have 1 pound. I put it on a scale. It's going to read out weight. What's the weight? All right, there's 3 answers. It's going to either read out around 32, 1, or 1 over 32 pound force. Pound force, pound force. Answer A. Oh, I wish we had our clickers. We'll get them. You'll be here tomorrow. True? Because I know some of you have had me before. I just give the same lecture. The university is so stupid they pay me again and again for the same lecture. Or if you had me before, it's first day of lecture. I usually cover things like this. Okay? So some of you know, and you need to be quiet. It's like, okay, I've had Monteufel. This is one of his fun things to do, So, but other students are like, I don't know you. And you tripped me up on that last question. No, I trust you not. I trust you not. Okay, I've got to try and regain their confidence, those students that don't trust me anymore. Is it answer A? Does 1 pound mass put on a scale in the United States in the presence of the Earth weigh 32 pounds? Or B, 1 pound mass put on a scale that rotates like this, that indicates pound force out, weight. Is it a weight of 1 pound force? Or is it 1 over 32? Let's do this. Which answer is most incorrect? C. Congratulations. You've saved a few people a really embarrassing hands up. I vote for C. No. Your friends have done you well. Now we're down to 2. It's a coin flip, 50-50. Who's brave? Are you brave? You're brave. Okay. A or B? B it is, and you are absolutely correct. You are absolutely correct. That's interesting that if I put 1 pound mass on a scale on the surface of the Earth, it indicates a weight of 1 pound force. So I can finish this equation. It's 1 pound force. True? Is that equation correct? You know what I can do now? I can go back and I can tell you the answer to the previous question that I avoided. I have to get this straight in my mind. I weigh maybe 180, okay? Right? I step on a scale. It rotates to show me 180. I could tell you my mass is 180 and my weight is 180. My pounds are 180. You want to call it pound mass? It's 180. You want to call it pound force? It's 180. Different concepts. One is weight, one is mass. But numerically, they have the same number. They have different units. Pound mass is not a pound force. True? True. But when I want to jump back and forth between inches, 12 inches, and feet, I use that one. When I want to jump back and forth between square miles of land and acres, I use that one. And you can think of a bunch of the other ones. We just played with one other one. This one you should tattoo somewhere on your body. Forget about tattooing. I love whatever. How many people, tattooed all sorts of crazy stuff? No, tattoo this one on your body. This is worth something. The unit conversion factor is 1 pound mass times 32.2 foot divided by second squared divided by pound force is precisely equal to 1. Got it? Got it. Where was the question that I dodged? This one. No. Where was it? I dodged it. I wouldn't answer it. This one right here. Is 1 pound force equal to 1 pound mass times a foot per second squared? I think we're building confidence. Some people say, that is a truthful statement. Raise your hand. Nobody's looking. We won't count it against you. False. Raise your hand. I still got some hands that are like, I don't know. This is not. This is false. It looks tempting. But just like this. How about this one? 1 inch is equal to 1 foot. Is that true or false? Students aren't going to fall for that one. Everybody knows it's 12 inches is equal to 1 foot. True? But somebody say, length is length. No. No. So anyway, to make this statement true, what do? Do I insert a 32.2 there or insert a 32.2 there? Answer A or answer B? Where do I put the 32.2 to make the equation correct? You're learning. This is great. You're learning. B. See? B. You put it in B. True? Doesn't it work? All right. Now let's continue on. Sometimes you'll see an equation. You'll say F equals ma. I learned that a long time ago. Newton's second law. True? Okay, good. Sometimes you'll say F equals ma divided by gc. What? What is this gc doing? First of all, if you see it, just take it out. Delete it. All it is a unit conversion reminder that says, don't forget. gc is precisely 1. That's all it is. Dimensionless. That's all it is. But it has a magnitude of 32.2, let me finish it off, pound mass, foot per second squared, pound force. It's just unit conversion unity. It's just a helpful reminder. It's old school to leave it in the equation. Don't be fooled. Professor, I learned slug is the appropriate unit for mass in the British system of units or the English system of units. You're not consistent with my textbook. How many people have heard of slug? In the United States, I stop a man on the street. I say, I'm sorry to ask such a personal question, but how much do you weigh? They could probably give me their weight in units of pounds pretty quickly. No, sir. Slugs. What's your unit of mass in slugs? You think what they're gonna do? Go up to a nice woman. You're gonna be in trouble. Slug, excuse me. All right, slug. What is a slug? First of all, the people in the United States customary system of units look enviously over the fence. The grass is always greener. To the SI system of units, and they look at the beauty, cleanliness, and all of that other stuff of 1 Newton is a kilogram, meter per second squared. They say, oh, I wish I had some unit of mass such that a foot per second squared times that unit of mass would be precisely 1 pound force. That's it. It's envy problem. Nobody in the United States uses slugs. There's a few people in academia that don't know what they're doing. They're called teachers. And they unfortunately have still perpetuated this notion that somehow you need to be, and I've seen it at UTSA, and I go around with them. They're like, oh, come on. No. 1 slug accelerated at a foot per second squared will occur, the acceleration will occur if you give it 1 pound force. Okay, imbalance. That's what it is. Okay, that's a slug. This makes it unity right there. But we already know that this is the one we like. True. That's the one we like. If you ask a person what's a slug, okay, on the street, they're going to say that some little thing that crawls in pavements, and unfortunately every now and then I step on them, and they crunch under my shoe. True? Or they come up and they leave a shell and do something else. What is that thing? It's a slug. That's what a slug is, a little animal we have pity on. All right, almost done. This is not used in the vernacular on the streets, in engineering either. Okay, professor, but let me do this. How many people still can tell me, though, what is my mass? I need to use the right term. It's not my weight. My mass in units of slugs. Anybody want to give it a shot? I'd take a brave soul. Who's brave? Daring soul. You're a daring soul. You're my victim. All right, you're looking at me. Tell me, what's my mass roughly in slug?
180 times 32.
Okay, so let's do this. You have a calculator? We can help him. 180 times 32. Somebody want to run that for me? So my mass, 5,760 60 slug. Okay, that's my mass. You are a brave soul. Now let's get the second brave soul in the class. Do I look like I'm 5,760 slugs or not? Are you agreeing with him? The second brave soul. I need a second brave soul. All you have to do is raise your hand.
180 divided by 32.
Oh, no. You have to raise your hand. There's my brave soul.
180 divided by 32.
Okay, can you give me that number? 180 divided by 32. 5.6 slug. Okay. Third brave soul? Or are we done? We're done, huh? We're ready to vote? We're ready to vote. Okay, how many people say I look like I'm a 5,760 slug mass? How many people say I'm a 5.6 slug mass? All right. How many people would say if I said, I want you to go give me something about the size of a slug? Where would you look for in this room for a size of a slug? A slug. Just say, yeah. This right here, this 5 sheets of paper is the mass of a slug. Right. No, that's not a mass of a slug. Come on now. Where are we going to look? Who's got a big, heavy book bag? Yeah. Big, heavy book bag. Right? That's a big slug. You see it every now and then. Poor student, strap humped over. So, 1 slug is equal to how many pounds? This is just trivia. It's not used in engineering at all. It's just trivia. How many pounds is a slug? About 30 pounds. 32. Right? Anybody picked up a book bag that weighs about 30 pounds? 14.3 kilos? 14.6 kilos. Okay. So about 15 kilos. Anybody does that help you? Somebody says, here's 15 kilos. Give you a sense of its weight or mass. Right? All right. Forget slug. I'm just having fun. We are done, I think, with Chapter 1. I do need to point out a few things, and I'm still going to lecture into Chapter 2. Format. When you have your final answer, you need to express it with something equal to something. It's an equation. You need an equal sign. Okay? And you put something like P2. I was asked to find the pressure at state 2 or location 2, something like that. Got it? And then you put your number, 300. But a number by itself is not very good in engineering. I need the units, kilopascal or PSI or something. Got it? Once I have the equal sign, something to the left, which is an expression that I'm looking for as part of the problem, L, A, P, T, whatever, equal to the magnitude with units, then I can box it. Put a box. Professor, is this a box? No. Is this a box? No. This is a box. All right. Now, it helps draw the attention to the person who's supposed to grade your work this is my declaration of my answer. What happens if I don't know the answer and I've worked it out 2 ways and maybe I can give you the answer and this answer too and box them both and let you pick the correct one? Don't do it. Okay. Professor wants a box. Here it is. There it is. My answer is in the box. No. 1 equal sign, something to the left, something to the right. Not 5 equal signs and 3 lines. Okay. The other is how many significant digits should you report your answer to? 3. 3. Got it? Go please read your textbook on significant digits. It's in your chemistry book, it's in your physics books, it's in your statics book, it's in your fluid mechanics book as well. Okay? So 3 significant digits. Why 3? You usually don't know things to 4. 3 is often stretching it. But we will gladly accept 3. We'll even on a test accept 4. But not 5. You lose points. It's to help you save embarrassment. How many people have already gone out and they've gotten a job somewhere, right? And then, oh, you're an engineer in training. Okay. You hot shot. Type of classes you take. Oh, thermo and heat transfer and fluid mechanics and statics and dynamics. Oh, you know something. I've been working at this company for 40 years. You guys always get hired in. Hire me. Pay scale. I'll ask him a few questions. They do, and it's one of those rites of passage. So anyway, you need to know some things, and I'm trying to save you the embarrassment of you going out and then reporting a number to 6 digits on your first report. It's embarrassing. You tell me your weight to 6 significant digits. You tell me Earth's gravitational traction or acceleration in this room. Do you know it to 3? Professor, it's 9.81. In this room, is it 3? Is that good to 3 digits G? Well, if it's not, then they should maybe go and redesign all the buildings and bridges in San Antonio when I find out that it's not 9.81, but it's 9.80. Shouldn't they? No. So you don't know G to 3 significant digits. Let me do a quick review of this chapter. We talked about what a fluid is, no-slip boundary condition. What's a layer near the solid surface? We call that the boundary layer. Talked about viscous flow, incompressible, Mach number, Reynolds number, laminar and turbulent. Talked about a review of systems, open system, closed system, dimensions, units, dimensional homogeneity. Use this to check your work. Unit conversion ratios. Be neat, be clear. How many people have messed up on unit conversions and then want a lot of partial credit? Do we have the concept of what mass is? Do we have the concept of what weight is? Do we can distinguish between the two? And do we have the concept of force? Newton's law, second law. Universal law of gravitational attraction between two masses. And then here is Earth's free-falling acceleration. 2 values of G that you remember, that you know. 9.81 and 32.2. True? Then we talk about weight, and then we have 2 new units. There's 4 in total G's that you should know. You should know G in the SI and the USCS as if it's falling. That's the G of 9.81 meters per second squared. That's the G of 32.2 foot per second squared. You should also know when things don't fall, because most of the times things don't fall. Things just sit and are supported because they have weight. All right? That G in the SI is 9.81 newtons per kilogram. What, Professor? G is 9.81 newtons per kilogram? Looks wrong to me. Is it wrong? Or is it right? And then the one that a lot of students will forget. G is 1 pound force divided by 1 pound mass. True or false? Makes life so easy. So somebody says, I want you to calculate the weight using this equation, mg. I can do it. I can do it with confidence. All right, I want you to do it and tell me the weight in pound force. And guess what the mass is? It's 18 pound mass. You know what G value I'm going to use to solve this problem? I'm not going to use 32.2 foot per second squared because it's not falling. I'm going to use 1 pound force is 1 pound mass into Earth's gravity. That's G. That's what G is. And then look at the weight of 18 pounds is 18 pounds. You look so smart when you do things quickly, right? Anyway, 4 values of G that you should know and be familiar. This is the least used. Nobody knows G is 9.81 newtons per kilogram. This is probably in the streets and around the United States the most widely used, widely known, easily remembered. And yet, in engineering, for some odd reason, we've forgotten it. All right. Dimensional homogeneity, I think I already mentioned that, didn't I? Unit conversion, I mentioned that. Significant digits, 3, make sure in box with an equation format. I've got a few minutes left over. Let me go ahead and stop recording.